Welcome back to this course on computational thermodynamics and kinetics of materials. Let's get to the next topic. Today we'll be seeing about phase diagrams, especially how state variables and phase equilibria are connected and how phase diagrams represent that. And we will see a couple of types, that is unary and binary. In binary we will see a simple type of phase diagram called isomorphous diagram, and we will see ideas like Solver's line, transformations in a phase diagram like allotropic transformation, melting, solidification and precipitation. Let's see about state variables and how they are connected to phase equilibria. These are actually thermodynamic state variables. We will see about thermodynamics in the later part of the course. So today we will see something about the state variables and how they are connected to phase equilibria. So let's think about a piece of nickel inside a furnace at 500 degrees Celsius. It has a FCC crystal structure. So in nickel at 500 degrees Celsius, single FCC phase is stable. So instead of nickel, if we have iron, at the same temperature we will have a BCC phase. Okay, so in iron 500 degrees Celsius, single phase BCC phase is stable. So here what is happening? The chemical composition is changing for the material. From 100% nickel it has become 100% iron. So chemical composition can affect phase equilibria. That's what we understand from this. So imagine we increase the temperature to 1000 degrees Celsius. What happens in the case of nickel is it's becoming hotter, but the FCC structure remains. Whereas in iron, it becomes hotter, but the BCC structure does not remain. It transforms to FCC. Okay. So in nickel at 1000 degrees Celsius, single phase FCC remains stable, but in iron, single phase BCC does not remain stable, it becomes FCC. Okay, so temperature can affect phase equilibria is the conclusion from this, right? So what is change in state? So later we will see that state is represented by state variables. In this case, composition and temperature. These are the state variables. Okay, that is changing in these cases. Okay, so the composition changes from nickel to iron. Temperature changes from 500 degrees to 1000 degrees Celsius. So state variables can affect phase equilibrium. That's what we understand from all this. Let's think about a slightly complex case. So you see this iron becomes FCC at high temperature from its low temperature BCC structure. So there should be a temperature at which possibly two phases exist together. In fact, that temperature is 910 degrees Celsius, where both BCC and FCC phases can be stable. So in these simple systems, pure elements itself, there is so much of variations possible in phase equilibria depending on the state variables. What if we have a map of state variables and corresponding phase equilibria? So the state variables, composition, temperature we have seen, even the pressure can influence phase equilibria. A map of this sort connecting state variables to phase equilibria is called as phase diagram. Of course, when we say composition, we are talking about all the elements in the periodic table, right? In what combination they are mixed and all. Then it's a huge space of variables. Okay, so what we will usually do is we will minimize the number of elements. Let's say at least one element, we'll call it as unary diagram or one component diagram. So we will reduce the number of elements, like one element, two elements, three elements. Within that we will keep the number of elements, and we will think about changing temperature and see how different phase diagrams appear. And if we keep the composition as just one value unary diagram, then we can change both temperature and pressure and look at what happens to phase equilibria. So that is possibly the simplest of the systems. So let's consider a unary phase diagram. Number of components are 1. For example, we will consider pure iron. So state variables are going to be temperature versus pressure. So this is the diagram that we are going to have. So let us consider the pressure, which is atmospheric pressure. Since it is in gigapascals in the x-axis here, atmospheric pressure in gigapascals is almost equal to 0.0001. Okay, so this is the x-axis, the pressure almost near zero is indicated here. At that pressure, at temperature of zero, it is in BCC structure. This is a schematic of its microstructure. So there are 3 grains of BCC. So what happens when the temperature increases? For a range of temperature, this BCC is stable. Then beyond a certain temperature, it becomes FCC, and it remains as FCC for a range of temperature. And this is the FCC microstructure. So once it reaches some other temperature, it becomes BCC again. So this is the BCC microstructure. And beyond a temperature, BCC finally becomes liquid. So in solid state itself, there are changes in pure iron. So once it becomes liquid, so this is the liquid structure, there are no grains. So there are 4 different phases at different temperature ranges. So what if we change the pressure to a slightly higher value? These transformations do happen, these phases do remain stable for a range of temperature, but that range changes slightly. Okay, if we increase the pressure further, again this transformation temperature changes, but that high temperature BCC does not appear at all. The FCC is stable till the melting point. So this BCC appears only near the atmospheric pressure. So what if we track all these transformation temperatures and create some sort of a map like this? So this is a phase diagram. So at really high pressures, we see a HCP phase forming. So these phases are not named like this, BCC, FCC, that is the name based on the crystal structure. And here it is liquid for high temperature phase. But this kind of names may not be there, may not be used in different places. So these Greek letters are used: alpha, gamma, delta, L for liquid, epsilon for HCP, like that. So these are single phase regions: alpha, gamma, delta, and liquid. So now what about the phase transformations that are happening in this system? BCC to FCC, again to BCC to liquid. This is happening at atmospheric pressure when temperature changes. These are called allotropic transformations in the solid state, the BCC becoming FCC and FCC becoming BCC. This can happen when temperature increases or when temperature decreases. So this reversible symbol is put here for that reason. So these are allotropic transformations. This happen in a few pure metals. So that is the iron is one such interesting case. That's why we considered it in this example. So melting is another kind of transformation happening here, also called as fusion, or the reverse of it is called as freezing or solidification. So in this atmospheric pressure case, you can see BCC becoming liquid, delta becoming liquid, and liquid becoming delta when the temperature decreases. So that is another type of transformation. So in pure elements, at a fixed pressure, the transformations occur at a single temperature and not over a range of temperature. If you see, all these temperatures are single temperature at which the transformations happen. Yeah, so this is the case in pure metals. When we go to binary and other higher order systems, this will not be true. Right. So only at the transformation points, 2 phases can be in equilibrium. So for example, at melting point, you can see along this line, both the solid and liquid are in equilibrium. Right. So the lines indicate a 2-phase equilibrium. So the lines also indicate the boundaries of single phase regions. You see, so you can see this line here, it is bounding this alpha region. So in a way, these lines are the boundaries of single phase regions, right? That is another way of looking at the diagram. So the lines are also used to identify certain relations. For example, how the melting temperature varies with the pressure, or how the alpha to gamma transition varies with the pressure, things like that. So you can see how a unary phase diagram gives so much of information about a unary system. So with this, let's go to binary phase diagrams. So in binary phase diagrams, the number of components are going to be 2. So this kind of diagrams are widely used for metallic systems, especially the alloys. What is an alloy? It's having 2 or more elements, predominantly metals, with possibly some amount of non-metals. In periodic table, we can imagine a line like this, which demarcates metals and non-metals. So what variables are we going to use for making the binary phase diagram? Pressure is not going to be used. It is ignored in most binary phase diagrams. Its effect is not important in most practical cases of alloys. So the binary phase diagrams are going to be usually temperature versus composition diagrams. So let's look at one such system. So let's imagine sugar water system again. So 220 gram of sugar, we said, can dissolve in 100 gram of water at 30 degrees Celsius. That is the solubility limit. This we have seen in one of the previous classes. So what happens when temperature changes? So the solubility limit changes. This 30 degrees Celsius 220 gram is, so this 220 gram is the solubility limit at 30 degrees Celsius in 100 grams of water. When temperature goes up to 100 degrees Celsius, as high as 500 grams of sugar can be dissolved in 100 grams of water. So let's do one thing. In this system, we are going to draw mass of sugar versus temperature, and we are going to choose these different temperatures 0, 20, 40, 60, 80 and 100, and we are going to track solubility limit in 100 gram of water. So we are going to take 6 different glasses of water with 100 grams each, and we are going to keep adding sugar into each of them, but we will be keeping them at different temperatures 0 to 100 degrees Celsius at 20 degrees intervals, and see how much is the solubility limit of sugar. So if we track that, we will be getting a diagram like this. So mass of sugar versus temperature. At each temperature, there is a red cross mark which tells that's a maximum amount of sugar that can be added. The y-axis shows the amount of sugar in 100 grams of water. So joining all these points, we get this black line. So that shows the solubility limit. So at any temperature, let's say like this 30 degrees, we can see that 220 grams is the sugar that is soluble. And anything beyond that will result in sugar plus solution plus sugar. Okay, so let us demarcate that at in this range, in this lower, in this range we have single phase solution possible. Anything beyond this line will have solution plus sugar. So in this diagram, if we rotate it and keep the temperature in the y-axis and mass of the sugar in the x-axis, we will see a line of this sort. So in this is the range over which single phase solution is stable, and beyond that solution plus sugar is stable. So this line here is called as Solves line. So the Solves line tells you what is the maximum solubility of one component into the other. So let's imagine a point here at this temperature, and at this temperature we have so much of sugar dissolved into the solution, and the same vessel, if it is brought down in temperature to a lower temperature value, we will be here, and now we are in the two-phase region, solution plus sugar. So what will actually happen? High temperature is a solution where sugar is dissolved, and when the temperature is decreased, we are going to get sugar coming out of that solution. So this kind of phase transformation, that is precipitation, will happen, and phase diagram quite elegantly indicates that. So now, is this the phase diagram? It is not actually the phase diagram, because in this the x-axis is the mass of one component, that is mass of sugar in gram. That's what we are using in the x-axis. But when we use this, does it have information on the content of water? We are simply putting 100 grams of water in the top just to indicate that is our experimental condition. Okay, in the x-axis we are only tracking mass of the sugar, so that is not indicating anything implicitly about the water content. So it is not informing anything. So let x-axis be the composition of the component, that is mass percentage of sugar, and not mass of sugar. So let us change it to mass percentage of sugar. So this is considering the water content as well. So what is a phase diagram? The mass percentage of the other component, water, should be implicit in that. 100 minus mass of sugar. 100 minus mass percentage of sugar. Okay, so in the x-axis right now we have mass of sugar varying from right to left. Instead we can keep mass percentage of water varying from left to right like this. It's up to us. So this idea of homogeneity range is given for single phase regions. You can see this entire region highlighted in blue color now is the homogeneity range for the single phase solution. Okay, so this indicates basically for what composition and temperature ranges this phase is stable. So this phase homogeneity range means that for a single phase. It's a quite important idea as we go along. So in a binary phase diagram, what are the axes? Temperature and composition. Composition can be indicated as percentage of B going from left to right or percentage of A going from right to left. And when we put pure A here and B here, it means that here the content of B is 0 and here the content of B is 100. Okay, so we are going all the way from 0 to 100. Right, let's look at one of the simplest of binary phase diagrams called isomorphous phase diagram. So this is how it looks. So there is only one solid phase here, alpha. Let's understand it from the atomistic scale, which is a better way to understand the diagram. Let's start with pure A. This is pure A atom sitting in some crystal structure. Let's call it alpha. And when the temperature increases, it becomes liquid. So there is no crystal structure there. So let's start the phase diagram with pure A and against temperature. It's going to be one phase alpha till some temperature, and beyond a certain temperature it's going to become liquid. Alright, so let's take B, which is having, let's say, similar crystal structure alpha, and it also becomes liquid at a certain high temperature. So let's track that as well. So this is content of B, means 100% B, and it becomes liquid at a particular temperature and stays liquid for a big range of temperature. Alright, so then this is, so what happens when B is added to A? Percentage of B, let's increase from left to right. So this is the atomistic picture where B atoms, the gray atoms, replace the white atoms, the A atoms. Okay, so you can see the content of B keeps on increasing from left to right. But what is important is the alpha structure doesn't change. Let's say this is some FCC structure, but that doesn't change as we keep adding B, and B is also in FCC structure. So we don't see any crystal structure change. It's just a complete solid solubility from going from left to right. So if we represent, so this entire region is alpha. So if we represent this in the phase diagram, we are going to have the x-axis with percentage of B, and the entire region is alpha. And this alpha is going to become liquid beyond a certain temperature, we know that. So possibly we'll put a line like this. Can we say beyond this line all the alpha will become liquid? The answer is no, because when alpha is heated beyond a certain temperature, it becomes alpha plus liquid. There is some liquid and some alpha. The same crystal structure is still remaining. So some solid and liquid exist together for a range of temperature. So let us call it liquid plus alpha region, and only beyond another temperature everything becomes liquid. So at some really high temperature, for all the compositions we will have liquid phase as the stable phase. So we said percentage of B can go all the way from 0 to 100. So we have complete solubility. So we can imagine the reverse also. We can consider this as taking pure B and adding A to that, replacing gray with white atoms and gradually making it completely A. So even this is possible. So in this case, what we are talking about is solubility of A in B, and it is also 100%. So this is where we use this term complete solubility of two components in solid state. So this is the feature of isomorphous diagrams. So you can go from pure A to pure B, it's single phase alpha stable, or you can start from pure B to pure A, it is single phase alpha stable, or even you can start with pure A and B, join them, let them diffuse into each other, it can also form single phase alpha, right? So this is how complete solid solubility works. And at high temperature it is complete solubility in liquid state, which is the case with most of the systems. Some systems show some phase separation in liquid state also. You already know some practical examples. The oil and water, they don't mix in each other, two liquids which are separate. In that case we will see different compositions of liquids are in equilibrium rather than one single liquid. So that's called as immiscibility in liquid state. We'll see about such concepts later. Which are the solvous lines? So we have seen solvous line in the liquid water sugar system. Here can we consider anything as solvous line? These two lines look like solvous lines. Taking, let's say, at this temperature pure B liquid and keep on adding A to that, we keep moving in this direction, and there is a point at which the single phase liquid is no more stable, it becomes liquid plus alpha. So this is like a solvous line. At the same temperature, if we consider the reverse, let's say from pure A we start, it's solid, and if we keep adding B to that, the same solid structure remains. Beyond a certain, this is becoming unstable and liquid forms. So these two lines can be looked at as solvous lines, but these are actually considered as liquidus and solidus temperatures because there is a liquid and solid involved in these lines. So what are these? Liquidus is a temperature above which everything is liquid. Solidus is a temperature below which everything is solid. So the atomistic picture we have seen, at low temperature it's all solid, and high temperature it's all liquid. As the temperature increases, we have this different phase equilibria coming. So only in alloy solidification and melting can occur over a range of temperature. Range of temperature is bounded by these liquidus and solidus lines. So in pure metals it occurs at a single temperature. You see this extreme ends where both the liquidus and solidus line converge. It means that there is only one temperature for pure elements where solid becomes liquid. It's not a range of temperature. So we have already seen the atomistic view. Let's look at the microscopic view. Let's consider different temperatures. At high temperature it's all liquid, and there is a temperature range over which liquid and solid are stable, and below temperature it's all solid. So how the microscopic structure looks, let's choose these three temperatures at this composition, and this is how microstructures will look. You see, at low temperature we have complete alpha, so these are all grains of alpha. And at high temperature we have liquid, everything is in liquid state, and in between, in this temperature region of liquid plus alpha, we have liquid plus alpha grains, liquid phase and alpha grains. So this is the microscopic view. So this is what you will see under a microscope. We have been looking at the atomistic picture directly, so this entire thing is inside a grain. I hope you remember that. So one has to imagine all these things together to understand the materials better. When you deal with materials, possibly you will be looking at the microstructures. You should be in a position to connect to the phase diagram and think about microstructures. And also, more importantly, you have to think about the atomistic picture, because this is where the entire thermodynamics and kinetics will come into picture in understanding the phase transformations and phase stability. So it's highly important that you develop the ability to connect these different aspects and be able to understand your material. So one important note here, phase diagram does not show what happens during cooling. You may think that as we cool, this is what happens. Strictly speaking, it may be true when we do slow cooling, But strictly speaking, it shows what happens when the materials attain equilibrium at each temperature. That's the meaning of phase diagrams. These are all equilibrium diagrams. They show phase equilibrium. That means at different temperatures, at different compositions, what are the equilibrium phases? Meaning you have given enough time for equilibrium to be achieved at each temperature. That's the meaning. So it's not that you cool at some rate and expect what you see in the phase diagram to appear in reality. Okay, your cooling rate should be extremely slow. Then there is a chance that you get a microstructures which are closely resembling the phase diagram. So with this we will stop. I hope the lecture is useful. See you in the next class.